So welcome to 8R Notes, which is essentially a company that provides high school resources for students to succeed. So we do provide a lot of free resources such as study notes, lectures, discussions, videos, newsletters, an 8R calculator, articles, and much more. There are thousands of study resources that you can find. Just visit our website. So this is a head start lecture for Physics 3.4, and we are going to cover a lot of things, but primarily we are going to go through the things that you need to know from units 1 and 2. Then we're going to go through the topic of motion, fields, electricity generation, which is part of what you learned the first half of the year. Especially with the new changes to the study design. And in the end, I will provide you with some tips for succeeding in year 12 and units 3 and 4 in physics. So today's goal is to give a brief overview of some of the topics encountered in unit 3. We don't have time to go through every detail. Just get a head start on the concepts today, and we can focus on the detail when you learn it through the year. Keep in mind the disclaimer: you can access the lecture recording and the slides. General guides to answering questions, things to know from units 1 and 2. Our aim is to teach you about Newton's 3 laws in this lecture, about constant acceleration formula, how to do vector addition, momentum and impulse, the concept of work, and gravitational string and kinetic energy. Now let's look at some examples of how to answer a question in the VCE exam, given that you're going to see the exam at the end of the year. So when it comes to answering calculation questions, sadly, you have to show every step of the working out. If you don't show every step of the working out, you will definitely be liable to lose marks. The reason for that is because VCA examiners cannot guess where you made a mistake. All they know is that you've made a mistake. So if you don't show your working out, me as an examiner, I don't know where you made the mistake, right? How can I help you if I don't know where you made the mistake? How can I give you more marks? All I know is the answer you have provided me is incorrect. So I cannot by virtue, right? I cannot give you I cannot give you any marks. However, if you do show me your working out, I can see that you made the substitution mistake, or I can see that you made the mistake in the final calculation of your answer. In that case, I can give you partial marks. I can give you partial credit. Also, I would highly recommend you, before you rearrange, you write the original formula that is on the formula sheet. So this is something I want to spend some time on, right? Before you rearrange, write the formula as it is on the formula sheet, then you can rearrange. For example, if you need to find velocity, you write this equation first, then you can rearrange for velocity and say, oh, well, it is equal to square root of AR, right? Whereas for extended response questions, it gets a little bit funny, because For extended response questions, it's a little bit harder to comment on how you should properly answer these type of questions, because genuinely no one really knows, right? Genuinely, no one knows what the VCA examiners actually want. So the best thing you can do in this case is to try and use dot points. And usually the general strategy that works for most people, and again, disclaimer, this isn't gonna work for every single extended response question, but it's a good rule of thumb to, first of all, explain the theory related to the question. Then put the theory in the context of the question and then make a final statement if necessary. And try and do this in dot points. When you use dot points, essentially what is happening is you are indicating to the examiners that, hey, look, you are indicating to the examiners that you are a diligent student that knows what you're talking about. And usually confidence is key, right? When you emit that type of confidence in your response, usually they are more prone to give you marks than not. So in this, sorry, I'm a little bit sick, but in this case you can see, explain why an EMF is generated in the wire loop as the magnet approaches the loop. First, you state that Faraday's law states that if there is a change in magnetic flux, EMF will be generated as voltage is equal to, and you give the voltage equation, so it's equal to n number of loops in the wire multiplied by changing flux over changing time. And usually the negative sign there indicates, and you can say that it is indicative of Lenz's law. As flux is equal to A multiplied by B, so area of the wire, area that is enclosed by the wire multiplied by the magnetic flux, sorry, multiplied by the magnetic field strength. If magnetic field strength changes, then the flux will also change, because they are dependent on one another. Hence, as the magnet gets close to the loop of the magnetic field strength increases, changing the flux and generating EMF. So usually, kind of that illustrates how to answer extended response questions. Personally, I would just say make sure to, most of the time I would say just make sure to put a little bit of the theory in and include a formula. So even if you're not sure how to answer an extended response question, usually that is a good rule of thumb. Now we are going to take some time explaining Newton's three laws of motion, because ironically, even though they are considered to be the easiest laws of motion, the easiest concepts in physics to understand, and students think they are super easy, sadly, we examiners have finally come to the realization that students don't actually understand the three laws of motion. They can regurgitate what they are, but they don't actually understand the three laws of motion. And they have been very recently, or the past few years, they've been consistently asking questions in regards to the laws of motion. And students have been consistently getting, providing incorrect answers. In particular to the third law, because that seems to, I mean, there has been improvement in students' responses over the years, obviously, but it's still very evident that students still make mistakes. So let's start with the first one. What does the first law state? It states that an object will remain at rest or travel with a constant velocity if the net force acting on the object is 0. Alright, so the reason why a lot of students don't actually understand the laws of motion is because there is the tendency online, and usually in online forums, to oversimplify things. And they do oversimplify things by using analogies which aren't really fit for the context. For example, they will say, well, if an object is doing something, it will keep doing that thing unless something acts on it, blah blah blah, that type of thing. No, that is the incorrect way to think about Newton's laws. That's the wrong mindset. You have to read the law very carefully and what it states. And this is what Vika does, right? It states an object will remain at rest, aka, or travel with a constant velocity, aka velocity is equal to 0 or velocity is constant. You have to think in mathematical terms. If the net force acting on the object is 0. The key word here is the net force, not force, the net force. For example, at the moment, I am not accelerating on the vertical plane. The reason for that is because the net force acting on my body on the vertical plane, now that I'm sitting on the chair, is equal to 0, right? There is a weight force by gravity pulling me down, pulling me down, but there's also the normal force applied by the chair and the ground combined together, pushing me up. The normal force that pushes me up is equal to the weight force that pulls me down. They cancel each other out. Hence, I do not accelerate in the vertical plane. Same thing for the horizontal plane. If a car is traveling at a constant velocity, it means that its acceleration, the net force as a result of its acceleration, equals the friction force, right? Hence, it's traveling at a constant velocity. Oh, that makes sense for people. So again, I'm sitting on, so if this is a chair, right? So if someone is sitting, like if I'm here, or you guys are sitting, the net force acting upwards on you is equal to the weight force, so they cancel each other out. Same thing for a car, right? When a car is at rest, that is velocity is equal to 0, obviously no force acting on the car besides weight force and normal force. But on the horizontal plane, no force acting. If velocity is constant, then it means the thrust force by the engine equals, so the thrust force by the engine equals the friction force. They cancel each other out, hence velocity is constant. If the thrust force is greater than the friction, what will happen is velocity will start to increase. That's why when you press the accelerator, velocity increases, because when you press the accelerator, what you're doing is you're increasing the thrust force by applying more acceleration. Now, some of you might be very astute and you might say, well, Ray, how come when my dad presses the accelerator on the car and he keeps it pressed, right? At a certain position, the car then reaches a constant velocity? That is a beautiful question to ask. And there is a really good answer for that if you search online. Basically, the friction and air resistance, so the force that they apply on the car, will eventually equate the thrust force. So for a car to keep reaching higher and higher velocities, you really need to press on that pedal, right? Like you really need to keep pressing on the pedal for the car to reach higher and higher velocities, because you need to constantly provide more thrust force. Cool. So that is the first law. Second law. The acceleration of an object is directly proportional to the force applied and inversely proportional to the mass of the object. AKA, as the mass of the object increases for the same amount of force, the acceleration will decrease. So it's saying this. It's talking about the rearrangement of the formula. And how do we think about this? All right, how do I explain this? If you provide the same thrust force on a car, but you increase the mass that that car is carrying, right, the cargo of the car, let's say a truck, for the same amount of thrust force, the truck will accelerate a little bit less, right? So the heavier an object becomes, for the same amount of force, it will accelerate less. And I really want you guys to not take these formulas at face value, but to actually think carefully about them and concentrate and try and understand them. However, the same thing applies if you keep the mass of an object constant, and usually this is more intuitive. If you keep the mass of an object constant, the more thrust force you apply, the greater the thrust force, it means the greater the acceleration, because obviously in order for you to get greater thrust force, you need greater acceleration to begin with. So we understand the direct relationship, but the inverse relationship is a bit less intuitive, but it should make sense. The heavier an object gets, the slower it can move for the same amount of force, right? Yeah, so the heavier the object is, if you increase mass, but you keep force constant, you have to decrease acceleration. For the same amount of force applied, if you increase the mass, or to get the same amount of force, if you increase the mass, you have to decrease the acceleration. That's a better way of putting it. And so usually when you make weapons, they think about the second law quite a bit, right? So how can you ensure that the weapon that you are building provides a lot of force? Well, one way to think about it is you can increase the acceleration of the bullet, and if you cannot do that with the current technology that you have, you can just make the bullet bigger, right? Or as big as you can without having to sacrifice acceleration. Yeah, and that will increase the amount of damage that you cause the enemy. Now, the third law, the most misunderstood out of all. If object A exerts a force on object B will exert an equal and opposite force on object A. What does that mean? So for the third law to make sense, and this is where 90% of students make mistake, not 90%, according to the VCA exam, 70% of students make a mistake, but I'm gonna assume the 30% that gets it right, usually there is a proportion of students that, even in that 30%, that don't know, they just guessed the right answer. So for the third law, you need to understand that what we've learned so far is actually, some of you might have learned incorrectly. So there's three categories, three key criteria. One, the forces to be action-reaction forces must be equal in magnitude, applied in opposite directions, and be of the same type. Or, aka, applied on different objects. Let me explain. So if we look at a car, right, or like, let's say there is this box, this block, this rock, whatever, on the ground, there is obviously a weight force acting on that block, what would be the reaction force to the block? What would be the reaction force to this rock? Most of you would say, oh well, it should be the normal force. It's equal in magnitude, it goes in opposite direction to the weight force. However, even though they are equal in magnitude and opposite in direction, the normal force is not the action-reaction force to the weight force that the Earth applies on the block. Because the reaction force has to be of the same, it doesn't have to be of the same type, but it needs to apply on different objects. For example, the reaction force to the weight force that the Earth applies on block B is the weight force that the block applies on the Earth. That is the reaction force. Right, it's the weight force that the block applies on the Earth. Does that make any sense? So these are action-reaction force pairs. So the normal force that the Earth applies on the block, the reaction force of that would be the normal force that the block applies on the Earth. Right? Earth on block. Again, block on Earth. Again, these are applied on different objects. So, if the object is at rest, the reason it is at rest, yes, it is because the weight force that is applied on the object is cancelled out by the normal force that is also applied on the object, because they are equal in magnitude and acting in opposite directions, but they are acting on the same body. That's why the net force acting on that body is equal to 0, because obviously they are equal in magnitude and act in opposite directions. But that does not necessarily mean that they are action-reaction force pairs. To be action-reaction force pairs, usually they need to be of the same type, but I need to emphasize primarily act on different objects. So physics, even though it might seem easy to understand, it can actually be quite complex as a subject. Even for these very basic concepts. Now let's keep going. Let's look at some constant acceleration formulas. So this is what you guys call a SUVAT or something like that. Yeah, SUVAT, that's what you guys call it. At the end of the day, it doesn't matter what you call it, just remember all the formulas. Super important. So there is constant acceleration formulas and there is zero acceleration formulas. So what is a zero acceleration formula, you might be wondering? Well, when acceleration is equal to 0, the only motion formula that you can actually use is velocity is equal to displacement over time. Because the acceleration is equal to change in velocity over time. So you need to have a change in velocity for there to be acceleration. And if the change in velocity, so the rate of change in velocity is constant, so acceleration is constant. So if velocity changes by the same amount for every second, then acceleration is constant. If the velocity changes more for every second, it increases more for every second, then acceleration is increasing. We do not deal with change in acceleration formulas at the moment, not in VCE Physics. But for constant acceleration, you can use the formulas given here. The key with these formulas is to remember to use the right units. Such as displacement is measured in meters, velocity, initial or final, is measured in meters per second. So U stands for initial velocity for those who don't know, and V stands for final velocity. A is acceleration in meters per second, and time is denoted as t, and it's measured in seconds. Now, usually SUVAT formulas are super helpful when we're dealing with projectile motion. And most of the time, VCA will actually test your understanding of the difference between constant acceleration formulas and no acceleration formulas by giving you a question about projectile motion. The reason for that, it's because projectile motion can be divided into two planes of motion. There is the vertical plane and there is the horizontal plane of motion. In the vertical plane, what will happen is the force due to gravity will act on the object. So if you're shooting a projectile, let's say a cannonball that you want to throw at the enemy, right? If you have a tank and the tank is shooting a cannonball or whatever, like whatever you call it, ammunition, what will happen is the weight force due to gravity keeps acting on that ball, right? On that cannonball. And it will keep acting on that object from beginning to end. Now, because there is a weight force acting on the object, and there is no, in VCE Physics we ignore air resistance. So because in the vertical plane there is only one force acting on the object, it means the net force is equal to that force, right? So if an object is shot on the air like a projectile and there is weight force but we ignore air resistance according to the study design, it means that the net force acting on that object will equal the weight force. That's why usually visual representation is really good in physics, right? It is a great idea to try and draw. It is a phenomenal idea to try and draw out, if you can, what you're thinking. Because when you illustrate the problem, it becomes much easier, right? The net force is equal to the weight force, and if since the weight force is equal to mg, it will be different from zero because the object has mass, right? And acceleration due to gravity near the surface is about 9.8 on average. So we have in this scenario a net force different from zero, right? Which means, according to Newton's first law, as we learned in the previous slide, the acceleration will be different from zero as well. In this case, the acceleration will be constant because of g, or virtually constant. It will equal to 9.8. And therefore, given that acceleration is constant, so we realize there is a net force acting on the object, which is different from zero. Therefore, we know the object is accelerating. At what pace? At g, right? So it's a step-by-step problem. We have to look at the problem step by step. We've shot a cannonball. What are the... Okay, we ignore air resistance. What are the other forces acting on the object? Only weight force. Okay, so there is a weight force acting on the object. Therefore, and that is the net force, is the weight force. Okay, so there's a weight force. What's the net force? The net force is the weight force, right? So that's the second step. You identify the forces. Second step, you identify the net force. Where is it going? It's going down. Cool. What is the acceleration given this net force? It is 9.8. That's the third step when you try and solve a problem. All right. So there is 9.8 acting on this object, but it's acting down, right? And it's constant. Which means on the vertical plane, of motion, right here, it has been drawn here, you can use SU-VAT formulas. How about the horizontal plane? So this motion, which is okay, so if we want to analyze the motion of an object which is shot at an angle, obviously there are other formulas that govern this behavior. But at the moment in VCE Physics, we are going to divide it into two planes. I should have said that first, right? We're going to divide it into two planes. We have just analyzed the first plane, the vertical plane. The horizontal plane is easier to understand because what will happen is you need to think, all right, in the horizontal plane, are there any forces? Again, we ignore air resistance. We do not do quantitative measuring of air resistance in VCE Physics so far. Well, there are no other forces acting on the cannonball horizontally. Therefore, no forces. Therefore, the net force is equal to zero by virtue, right? No forces, first step. Second step, net force equal to zero. Acceleration equal to zero. If acceleration of an object is equal to zero, what did the first law say? The first law said if acceleration is equal to zero, an object will either be at rest or it will keep traveling at a constant speed. So for the vertical plane, we know acceleration is constant, which means velocity is continuously changing. But not for the horizontal plane. For the horizontal plane, acceleration is equal to zero. Therefore, for every unit of time, velocity is the same. It's either zero if the object is at rest, but if the object is already moving, it's constant. That means that from the beginning of the cannonball motion, right, from the moment it was shot till the very end, horizontal velocity will be the same. And how do we calculate horizontal velocity? By using v is equal to delta x on t. All right. Now there has to be some qualitative interpretation of air resistance, you might be thinking. Well, yes. In VCE Physics, you will be required to recognize that air resistance will reduce, the presence of air resistance will reduce the height and the range. So that's the qualitative answer to that. How do I put this? So the idea is, right? Vega will ask you a question. The worst question to possibly ask is to find the final velocity. So you know the initial velocity because it will give you 90% of the time. 90% of the time it will give you the initial velocity of the projectile. But it will not give you the final velocity. So this is when the object is first shot. Then after some time passes, the object will be like that, right? Hence the name of projectile. It begins and it ends. So Vega will require you to find the final velocity. How do you find the final velocity? Well, obviously you need the horizontal velocity at the end and the vertical velocity at the end. Then you can use Pythagoras theorem to find the hypotenuse, right? So square root of a squared plus b squared, right, gives you c. Okay, so final velocity is going to be the square root of a squared and b squared. Pythagoras, right? You can find this using Pythagoras, but first you need this, you need the horizontal and you need the vertical. But you already know the horizontal velocity from the beginning. So if Vega gives you the angle and the initial velocity, you already know the horizontal velocity. Why? I told you why. Because horizontal velocity doesn't change. There is no force acting on the object on the horizontal plane. The net force is equal to 0. Therefore, acceleration is equal to 0. So again, net force equal to 0, acceleration equal to 0. The object's velocity must either be 0, or if it's something, it's the same for every single unit of time, right? By definition. So the object's velocity is the same at the beginning and it's the same at the end. For vertical velocity, yes, then you have to apply SUVAT formulas to try and find vertical velocity. To find vertical velocity, it gets a bit more complicated. But how do you find, and you'll learn a lot of formulas, a bunch of formulas, but how do you find horizontal and vertical velocity given the initial velocity and given an angle? Well, if you are given an angle theta, let me clear it up a little bit. If you are given an angle theta, and this is the initial velocity, if you're given this angle, how do you find horizontal and vertical velocity? Well, vertical velocity, right, Vy, think about it this way. Sine theta is equal to vertical velocity, right, over hypotenuse, over the initial velocity they've given you. And cosine theta, you're going to use trig, is equal to Vx on V. So how do you find Vy and Vx? Well, Vy is equal to Vi sine theta, right? So initial velocity sine theta, or Ui I should say. And Vx is equal to initial velocity cos theta. But the element that connects the vertical plane with the horizontal plane is actually time. It's the only dimension that it's the third. It's actually, we call time the fourth dimension, actually, to be honest with you guys. So it's the fourth dimension that will connect the other two. Crazy stuff, right? And again, this is what a projectile looks like. Vertical, horizontal is the same. So you can get an intuitive sense of what's happening, but usually it's good to combine intuition with the actual formulas. These are just slides saying, usually I don't rely on the slides to regurgitate everything. I try and use them to support my explanation. Let me see. Let me see how much time we have. We've got quite a bit of time. Cool. All right. Yeah. Fair enough. By the way, I know like my face might block some of the stuff I write down, but yeah, it's fine. Like, it's not a big deal. I don't. Actually, I'm thinking, why don't they make us like we can just put a camera at the top here? Well, fair. So key points of projectile motion where the object is in the air and under the influence of gravity. The only force acting on the projectile on the object is gravity, excluding air resistance. The horizontal and vertical velocities are independent of each other. The horizontal velocity is constant, and the vertical velocity changes due to gravity, but the acceleration is constant. Hence, any of the constant acceleration formula are applicable. Remember, forces are vectors and vectors can be added. When dealing with forces, we use a lot of vector addition and Newton's second law. So we will review inclined planes and tension. Now, when it comes to inclined planes, there is usually a lot of there is a lot of confusion between inclined planes and banked inclined planes and banked tracks. So what is an inclined plane and what's the difference with banked tracks? That's something we need to cover. So two forces act on an object on an inclined plane. So an inclined plane is basically any surface that is raised at a particular angle, so it's not flat. And usually the forces acting on the object are the weight force and the normal force. Now, the key, usually Vika will ask you guys to draw what's happening. So usually the normal force is this one. I know I drew it very horribly. It's not wiggly, it should be straight, but I get it. Like, guys, you need to understand, like, my hand cannot draw stuff straight. And that is the weight force, right? So the normal force acts perpendicular to the surface, and the weight force acts from the center of body straight down. Now combined, these forces will provide the net force. If you were to combine it, they will provide the net force that is going down. Now, these forces can be then rearranged. Okay, the slides have the drawings themselves. These forces then can be rearranged to find out more about what is happening. Now for a banked track, let me emphasize this. For a banked track, you need to draw a force acting towards the center. All right? That's the difference. Because the banked track is raised at an incline which is called I forgot the name of the angle, but it will result in the design speed. It's a speed where essentially an object will not need the force of friction to move. It will only need a normal force, and as such, the centripetal force acts towards the center. So, again, be very careful, look at the context of the question. At the end of the day, if it says banked track, you think of things going to be applied towards the center, and if it's inclined plane, things are being applied perpendicularly. Things are sliding down. By the way, the weight force here is going to be mg sine theta, right? The weight force with this inclined plane is equal to mg sine theta. Okay, so now we're moving on to stuff that is a little bit more difficult, because we're moving on into the tension topic. So the topic of tension is the tricky one. And the reason it's a bit of a tricky topic, it's because tension can be an action-reaction force in of itself. So tension is the force in a rope or object that is created when something pulls on it. Many people struggle with tension questions. Questions asked in physics are often interested in the magnitude of tension. The best way to illustrate this is through an example. So, how do you deal with the fact that tension is a bit hard as a topic? Well, you do what most people do. You always draw a force diagram. First, find the acceleration of the entire system. Look at the system as a whole. Once you have the acceleration, use Newton's second law to find the tension and look at an individual component. This works most of the time, so if you're stuck, give it a go. And also be very careful with the signs and directions. So usually with tension questions, what will Vika ask you guys about is they will ask you about the pulley system or something similar to that. So usually Vika will ask something along these lines. There is going to be some sort of a table, a pulley system here, a block here, and a block hanging. Let's call the hanging block mass 1, the block at the top mass 2. So the thing is, Vika will first ask what's the acceleration of the body. This body, because they are connected with a rope, we call it a connected body. So what are the forces acting on this body, right? If we treat this as a connected body, what are the forces acting in there? Assuming there are no friction forces. Well, obviously, the only force is the weight force, right? Again, step by step, what are the forces here? Well, it's only weight force, right? So what is net force? Net force is weight force plus or minus nothing else. So the net force is the weight force. It's mg, alright? Plus or minus nothing else. There's no other force acting. No other force. Therefore, the net force is mg. Therefore, ma is equal to mg, a is equal to g. So acceleration, no, mistake. So ma is equal to mg. Again, the net force is the weight force. And that's it, right? So the net force on both objects is equal to mg, right? Because weight force is mg. But what is net force in itself, right? Net force is ma. So ma is equal to mg. But this m for net force stands for both bodies. This one, the weight force is m1g. Because that's the only block that the weight force is being applied to, that it's pulling it down. So, acceleration is equal to mg divided by this m here. This m is m1 plus m2. Oops. m1 plus m2. Then Vika might ask you what is the tension force on that case. So the tension force will be equal to the mass of the second object multiplied by the acceleration that you found. So the tension force will be m1, m2, right? Because acceleration was m1g divided by m1 plus m2. So m1, m2g divided by m1 plus m2. Now we move on to another topic called energy. Now, usually for the topic of energy, things get a bit more interesting. Because you are going to learn about 3 different types of energy. There is gravitational potential energy, which is equal to mgh. There is kinetic energy, which is equal to half mv squared. And spring potential energy, which is equal to half k delta x squared. The variables are mass in kilograms, gravitational field strength, height in meters, velocity in meters per second. There is the spring constant, and extension and compression. There is also the law of conservation of energy for an isolated system, where basically the total amount of energy is conserved, but it can be transferred or transformed. So the idea is, when it comes to energy, there is something we call the mechanical energy. So when you sum these guys up, right, you get something called the mechanical energy. The idea is you learn about gravitational, kinetic, and elastic potential energy, but you need to understand that energy cannot be created nor destroyed. It can only be transformed from one form into another. And what does that mean? What does it mean for energy to be transformed from one form to another form? Well, for energy to be transformed from one form into another, it means it must gain. In order for it to gain something, it must lose something else. Now, work, there is this idea between, we have this problem between energy and work, right? So the idea is the question is, what is work? Work is change in energy. Well, what is the energy? Energy is the ability to do work. So this is how usually most people define it, right? This is how most people usually define the difference between energy and work, which is kind of crazy. It is kind of crazy, right? Yes. So, when it comes to studying about energy, you need to realize that energy is area under the force distance graph. But that is also work. If that makes any sense. Because work is defined as the change in energy. So energy is the area under force distance graph, but this is also work. So work and energy are measured by the same unit, joules. Now, oh yeah, Hooke's law, springs, right? The next big thing. So when it comes to studying springs, things can get very, very tricky. So springs, first of all, the main equation to know about springs is that force is equal to negative k delta x. So that is the main equation to know about springs. What it is basically saying, it is implying that the greater the amount of force that the amount of force that the spring applies on you is proportional to the amount of force that you apply on the spring, right? That's what the negative is there for. It's there to indicate action-reaction force pairs. Now, k and x, so k is constant, right? It's a coefficient. It indicates stiffness, right? The greater the value of K, the more stiff a spring is, the greater the amount of force that you need to apply to change it by a little bit, right? By a centimeter. X stands for displacement, so whether you compress or you extend the spring, right? Yeah. Now, the area under a force extension graph, which is essentially us drawing Hooke's law, right? Is the elastic potential energy stored in the spring when the spring is either compressed or when it is extended. And usually when you learn about these three types of energies, kinetic, gravitational, and elastic potential energy, VCAR prefers to ask you guys about oscillating springs. So it doesn't have here an image of an oscillating spring, so I will draw that for you. So an oscillating spring is a spring that moves up and down. Yeah, that's an oscillating spring. And then it goes up and down. I think you guys get the point. So the idea is, at the beginning, so where the spring is at its resting length, there's only gravitational potential, and so assume the beginning is the spring at its resting length, alright? And assume the end here, at position number 3, the spring is touching the ground, right? So if we are assuming those key criteria, basically what you can think about here is that at the top there is maximum gravitational potential energy because that maximum height that the spring is raised above the floor. Midway through there will be maximum kinetic energy, and at the bottom there will be maximum elastic potential energy but no gravitational potential energy and no kinetic energy. So at the beginning the total mechanical energy is essentially gravitational potential energy, but as the mass drops, it starts to lose that gravitational potential energy, but that energy does not dissipate, right? It gets converted into another form. It gets converted into kinetic energy, and then it gets converted into elastic potential energy. Yeah. So at the top, the only formula you need to use is mgh, midway through is half mv squared, and at the bottom half k delta x squared. So no, midway through is a combination of 3 actually. Yeah. But half of the energy is mv squared. So each of the other ones are usually a quarter, usually. Now the idea here, the cool thing about this is that, yes, so this is gravitational potential energy dropping, elastic kinetic energy reaching a peak midway through, and elastic potential energy peaking out. But there is a mechanical energy. So if you've done addition of ordinates in mathematical methods, and you don't even have to have done that, you can just understand that if you add all the points together on the first graph, you will end up with a straight line. That will end up being right about here. That is what we call mechanical energy. Right? It's always the same, it's constant, because energy cannot be created or destroyed, it can only be transformed from one form into another. And then obviously there are the forces, so the weight force is constant all the time. The spring force increases as the spring gets extended, and then the net force obviously is something in between the two, and it's equal to 0 midway through. That's where obviously when it equals to 0, right, that's when acceleration is actually the greatest. No, not really. Yeah, because it reaches peak velocity. But when it reaches peak velocity, acceleration is actually equal to 0 because the net forces sum up to 0. which is an interesting, yeah, interesting thing that happens. Then you guys learn about momentum. So momentum is an interesting case where we essentially learn about the law of conservation of momentum. Momentum is basically mass multiplied by velocity. I love the idea of momentum. Actually, I love the topic of momentum. It's an easy topic. With momentum, it's mass multiplied by velocity, so it's mass in motion. It measured in newtons per kilogram, but it can also be measured in kilograms meters per second, because it's mass multiplied by velocity, obviously. There is a law called the law of conservation of momentum, that momentum before collision is equal to momentum after a collision. You're gonna learn a lot about momentum. It's an easy topic. But initial momentum is equal to final momentum. So when two objects collide, let me draw this out. So if there's object A and car A driving with a particular velocity and it hits car B, which is at rest, after the collision, car A and car B move together, right? So the idea is that mass of A multiplied by initial velocity of A plus mass of B multiplied by initial velocity of B is actually equal to mass of A plus mass of B multiplied by the velocity of both, right? So yeah, that is momentum, and that is the law of conservation of momentum. Usually there are different forms that this can come across. A and B collide, and then A and B move together. They collide, and then they move in opposite directions. So yeah, they collide and they're not connected, but they still move in the same direction. It can come in different forms. But there is also something called impulse, which is essentially a measure of change in momentum of an object when a force acts on it. So impulse is something quite interesting. Because we define it as a change in momentum, but we also give it the formula force multiplied by change in time. Yeah, I'm trying to also think another way. I'm trying to derive what's happening here. So, mass multiplied by velocity is equal to force multiplied by change in time. I was thinking, well, another way of saying it is, well, force is ma multiplied by change in time, right? But that is change in velocity over change in time multiplied by change in time, right? So that's one way to prove it, right? That impulse is equal to change in momentum. Again, not momentum, but change in momentum. So the change in momentum can be different from zero, but initial momentum and final momentum have to equal. The initial momentum and final momentum of the system has to equal to has to be the same. So the difference between the initial momentum and final momentum of the system is equal to zero, but of each individual object is not necessarily equal to zero. And that right there is the key, right? Because it means that if we want to reduce, and this is when you learn about crumple zones in cars, if you want to reduce the impact on an individual during an accident, when they have a car accident, you try and create crumple zones in cars so that it increases the time of collision. Because apparently, force is equal to impulse over change in time, right? So if you increase the time of collision, you reduce the amount of force applied on the individual for the same amount of impulse. So for the same change in momentum, by reducing the force, by increasing the time, you can reduce the force. And if that doesn't make any sense, what's this? It is acceleration. Oh my goodness, so many derivatives here. So by reducing the time, you're actually reducing the acceleration, which reduces. So you're reducing the acceleration with which the object changes its velocity, therefore you're reducing the acceleration, therefore you're reducing the force. Ding, 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 ding. So if you followed through what I just did, you would realize that is a good derivative. Oh yeah, one way to do this is like you can try this with an egg. You can hold up a blanket, have like a couple of friends hold up a blanket and throw eggs at the blanket. The egg will not crack. Now, obviously, there is this idea of the difference between elastic and inelastic collisions. So basically, a collision is elastic if the kinetic energy before and after the collision is conserved, and it's inelastic if the kinetic energy is not conserved. Now there is also something called circular motion. Now circular motion is basically an object which is moving in circles. When the object is moving in circles, we say that there is a centripetal force acting on it. Now the centripetal force is not a different force, it's just a force, right? It's not a special type of force. Friction can be a centripetal force. a centripetal force is just a net force. It's a combination of other forces that result in the object moving in circles. But the cool thing is that acceleration is equal to v squared on r, and we call that centripetal acceleration. We can come back to that. But yes, it can be a friction force. It can be the force when you're going up or down a hill, because again, it's a net force, the difference between the normal force and the weight force. And it gives you the idea that sometimes when you're moving up and down a hill, it gives you the idea that sometimes you're lighter or heavier than what you actually are. Because this, okay, so just caution. I know Vika is not a big fan of these words, apparent weight, apparent weightlessness, and true weightlessness. But it is very easy to use them to describe what's happening. So apparent weight is what you currently feel like. Apparent weightlessness means that it occurs when the normal force is equal to 0, and true weightlessness when the weight force is actually equal to 0. So why is there such differentiation between the two? Well, our conception of weight is actually the normal force that comes from the ground. So if that is equal to 0, we feel like we have no weight, but that's not the case. True weightlessness only occurs in deep space. And this is backtracks, so yeah. This is what I was talking about before. A band track is a little bit different from an inclined plane. Yeah. You can do this question. I mean, the formula is right there. Done. Okay. Ignore those slides for a bit. We're not going on a break. We're just going through fields a little bit, and then electricity, which is a really cool thing to talk about. So let us get started. Let me see how much time we have. We still have a decent amount of time. Yeah, we have like 20 minutes. So let's start with fields. So what is a field? A field is, effectively speaking, a 3D region of space. A field is something that alters a region of space. When two fields interact, they apply a force on each other. How can we represent a field? Well, we can use vectors. Vectors only applies to one point in a region of space. The direction of the arrow indicates the direction of the field. Length of the line determines the strength of the field, and field lines applies to large region of space. The shape of the line shows the shape of the field. The closer the lines are, the stronger the field is. Note that the lines can never touch. A field that is created due to mass. When two gravitational fields interact, there is an interactive force between the two masses. The properties with gravitational fields is that they are only attractive, they are a monopole. The shape is radial, the arrows point inwards, the field is strongest near the mass. the formula that we use is G is equal to Gm on R square, and Fg is equal to G capital M lowercase m divided by R square. So with fields, with fields, there are just different types of fields, basically. There's gravitational fields, there is electric fields, and there is magnetic fields. The idea is that these fields, since they are a 3D region of space, they will apply a force on any other field of the same type that interacts with them. Basically, we try and divide them into the type of interaction that they provide. For example, are they monopole? How many poles they have? Are they unipolar, dipolar? What is the shape of the field? Is it radial, so does the field lines get more concentrated toward the center? Because if that's the case, then the field gets stronger towards the center. If not, then they get weaker. So usually the density of the field line is an indicator of, visually it's an indicator of the strength of the field. Now, when we're learning about the gravitational field, obviously gravitational fields, we also learn about satellites, right? So usually, like the moon is a satellite of Earth, and the only reason it revolves around Earth is because the moon itself has a gravitational field which interacts with the Earth's gravitational field. Therefore, a gravitational force is applied on the moon, keeping it in orbit around Earth. Now, this is an example of a radial field. And this the force that acts on it is actually a centripetal force. So we combine the centripetal force with the weight force to derive something that we call Kepler's law. Now the weight force that we are going to use now is going to use a different equation. The weight force now, since we're learning about gravitational fields, is going to be equal to Gm on R square, where G is a universal gravitational constant and R is the distance between the centers of two objects, right? Now, keep in mind that the gravitational constant, again, it's a gravitational field strength, it's going to be this part. If you multiply it by the mass of the satellite, so big M, capital M is the mass of the main body. If you multiply it by the mass of the satellite, essentially speaking, you're just going to get the weight force acting on that object at that particular height above the surface of the Earth, or the surface of any other body. There are two types of energy associated with an object in orbit: gravitational potential energy and kinetic energy. These amounts change when the radius of the orbit changes. Normally, again, we use U equal to mgh to calculate gravitational potential energy, but because the value of G is constantly changing, the only way to calculate gravitational potential energy is to calculate the area under a graph. Because if you remember, just like with springs, the area under a graph is work, it's changing energy. So if the moon drops in height, we can calculate how much gravitational potential energy it has lost and how much of that energy has been converted into kinetic energy. Now, when we're analyzing a graph, you need to make sure here is where Vega tries and get to. So you need to make sure that is force and not gravitational field strength. If this is just gravitational field strength and this is distance, try and after you find the area, try and multiply it by the mass of the satellite. At the end of the day, make sure to also look carefully at the labels of the x-axis, because that's an indicator of you making, usually that's where students make a mistake. Now, my favorite is when we talk about electric fields. So the idea with electric fields is that they are dipolar. There's a positive pole and there is a negative pole. I love electric fields because obviously as a result of electric fields, we are where we are today, right? It propelled humanity forward. So electric fields can be both radial, but they can also be uniform. The beauty is that just like gravitational fields, they have something very cool, like the gravitational constant is equal to gm on r square. The electric constant, right? So the gravitational field strength is equal to gm on r square, but the electric field strength is equal to kq on r square, where k, just like g, is a constant. M is mass, Q is charge. It's the property of the field that we're studying, right? And R is the distance between the two radius, right? From the center of the two bodies. Now, obviously, we don't use meters. We use newtons and coulombs as newtons per coulomb as a unit of measurement of electric field strength. But the cool thing about electric field is, first of all, you can study centripetal motion because obviously an electron revolves around a proton. But at the same time, it is very cool because you can actually generate a uniform electric field. That's what's epic about it, right? Yeah. And in that case, we studied the fact that work is equal to charge multiplied by voltage. And yeah, and the reason for that is because voltage is equal to energy per coulomb, right? So you just remove the charges and you end up with energy. And what did we say? Work is equal to change in energy. So that's the derivative there. Magnetic fields, on the other hand, are epic if you combine them with electric fields. So magnetic fields, you guys know, they are only dipolar. If you break a magnet in half, you're going to get to smaller magnets. The thing with magnetic fields is that when you combine them with electric fields, they can be super epic, because apparently a charge in motion, right? Okay, let me finish magnetic fields actually. Magnetic fields, I get really excited, that's why I talk a bit fast now. Magnetic fields are actually equal to, so the magnetic field is going to be equal to QVB, so the magnetic force is equal to QVB, or NLIB, right? You're gonna learn more about this later. But B is essentially the magnetic field strength, alright? It has a north pole and a south pole. When you combine the two poles, they attract each other. So two poles that are the same repel each other. If they're opposite, they attract each other. Yeah. Now the beauty is if you combine it with an electric field, right? So a moving charge, like in a current, will induce a magnetic field around it, right? So every single wire in your house right now is inducing a magnetic field around it. The magnetic field, it's going to look something like that. And if you're following the direction of conventional current, the magnetic field should wrap around. Here you learn about the 3 right-hand rules. but you're gonna learn more about the three right-hand rules later. It's essentially they are used to help us understand where the force of the magnetic field is going, right? Where is it being applied? So it uses something called the dot product. But what I want to cover here is, after we talked about the three fields, the gravitational, electric, and magnetic field, which is kind of similar to talking about different types of energy, right? The cool thing about fields, especially magnetic and electric, when you combine them, is that you can actually generate electricity. So if you put two magnets and a coil in between them and you just turn the coil, an electric field, an electric current will be induced within them. What you see in the image is what I said before. It's just you combine electricity and magnetism to create a centripetal motion. That stuff is not that cool. What's cool, we can go back to that. What's cool is the fact that you can induce electricity from magnetic fields. That's the cool stuff, right? Because if there is a and I want to continue what I was saying, that's why I skipped some slides. If you can induce a magnetic field from simply current going through a wire, what happens if you coil a wire around a piece of metal, right? If you coil a wire around a piece of metal, like a bar, let's assume this metal is just a simple metal rod, right? If you just coil up, if you use a wire and then you coil it around, right? What will happen is you have just created a magnet, because remember, a straight coil, right, a straight wire will induce a magnetic field if electricity goes through it, right? But what happens if you have multiple coils, if you have multiple wires, right? What happens if you have multiple wires? What happens if you turn so by calling it up, you're essentially creating multiple wires, right? What you do in that case, you've created an electromagnet. You have created a magnet. You have magnetized the metal with the north and the south pole. You use the three right-hand rules. We're going to cover that in our next lecture. But you can you can create a magnet, right? An electromagnet, which is really cool. So if electricity can generate magnetism, can magnetism generate electricity? And the cool thing is, the answer is yes. If you rotate a circular coil around two magnets between two poles, what will happen is electricity will be generated. And that is what we call generators. But bear in mind, there is a difference between motors and generators. If you're already running currents through a coil between two magnets, then the coil will turn by itself. Therefore, you have a motor which converts electrical energy into mechanical energy. However, if you mechanically turn the coil without switching it on, with no electricity, if you're mechanically turning the coil, right, between two magnets, you will generate electricity. So it's really cool. So you can convert electrical energy into mechanical energy, but you can do the vice versa. You can convert mechanical energy into electrical energy as well, which is epic. Now, at the moment, you're in the very early stages, but when you learn about all this stuff, the three right-hand rules, how everything turns, very soon, like at the end of university, if you pursue physics, you'll realize the importance of the statement that energy cannot be created, it can only be converted from one form into another. As basic as that rule sounds, it is actually a very, very important rule. Something we cannot really ignore. What else do we have here? Magnetic flux. So magnetic flux is something you will learn more later on. But with magnetic flux is I like it, but I hate it as well, right? I like flux, but I hate it too. The reason for that is because it's a bit complicated. So usually people, what they will do is they will combine the idea of flux with the flow in a river and all of that. So it takes a bit of time to understand flux and Lenz's law. You need to cover, first of all, you need to understand fields very well. Then you need to understand motors well. After that, then you can move to understand flux. The purpose of us teaching flux is so you can understand the change in flux can generate voltage. And that's how a generator works, right? So you kind of need to see it from a top-down point of view. You need to learn, when it comes to this area of physics, you need to have a top-down point of view. You need to say, okay, cool, what am I learning about? I'm learning about motors and generators. Cool, so motors, we convert electrical energy into mechanical energy. Generators, we convert mechanical energy to electrical energy. But how do we do that, right? But in physics, what we do is we start teaching you about flux. So we start here and then we keep talking, blah, 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 blah. And people, students, are lost. Students are completely lost. Why? Because they lose sight of what they're learning. There is a difference between motors and generators. They look similar, but in principle, they operate differently. That is why I highly recommend you learn about gravitational fields, electric fields, magnetic fields, and motors separately. Then you start focusing on generators as a different topic, because then you're going to learn about flux to understand how a generator works. You're going to learn about, like, you need to learn the first about motors first, but then you need to learn about flux, EMF, the generator itself. Then you're going to learn about transformers, which can step up and step down voltage in order to save power, right? So, and with generators, you will learn that, well, okay, flux is magnetic field lines going through a certain area, right? So there is something called flux when you put a circular coil between two magnets, right? Because of magnetic field lines going through there. And essentially, if you rotate the coil, you're essentially changing flux over a particular amount of time. Depending on the number of coils, you will create a certain amount of voltage. Now, this voltage output can either be AC or DC, depending on the type of commutators that you're using. You're either using a slip ring commutator or a split ring commutator. So electricity is generated here, and then what's the output? Well, you can control it. You can either make it continuous or discontinuous, AC or DC. But it takes a bit of time to understand them. You need to understand how it actually works. You need to understand Lenz's law. I have provided you guys with the slides if you are interested. But if you want to learn more about physics, I would highly recommend you join my class, because these are really deep concepts. And yeah, I really like to go in detail about things, as you saw from my first half of the lesson. I go into a lot of detail, and I can explain, I think, this topic very well. Most of my students get above 40 study score raw, so up to you guys. But my tips for E12 will be just practice. Do as much practice as you can. Be organized with your time, and just be realistic about the work that you have to do from day to day. I think that's the problem that most students have, being realistic about the amount of work that they have. Tips for 3-4 physics. I mean, I have a bunch of tips here. I would say make sure you know your scientific calculator. That's my main tip, right? My main tip is make sure you know your scientific calculator. Make sure you're comfortable with it before you sit the exam. Don't try and change too many calculators. And also make sure you have the cheat sheet ready before the exam. That's something a lot of my students forget to do, but they still do well, so that's all that matters, I guess. If you ask